Welcome to lecture 4. This week I'm going to be talking about determinants. We'll start with an introduction to determinants, and then we'll see how to evaluate determinants by using row reduction. We'll talk about the properties of determinants, and then we'll finish by talking about Cramer's rule. So first, an introduction to determinants. Let me just remind you that if we have a 2 by 2 matrix, this is invertible if and only if the special number AD minus BC is not equal to 0. This special number is called the determinant of the matrix. And we can write this in two ways. We can either write det of A, or we can change the square brackets in the matrix to vertical lines. This week it's time to generalize this idea to all square matrices. In today's lesson, almost all of the matrices we look at will be square matrices. So unless I specifically say otherwise, anytime we have a matrix, assume that it's a square matrix. Why? Because only square matrices have determinants. 1 by 1 matrices are easy. The determinant of 1 by 1 matrix A11 is just the number A11. 2 by 2 matrices we also know how to do. What about bigger square matrices? First, we need to introduce two new concepts. If A is a square matrix, then the minor of entry Aij, which we write as capital M subscript Ij, this is the determinant of the submatrix that we get if we delete the ith row and the jth column from A. And then after we've got the minor of entry Aij, we can get the cofactor of entry Aij. Cij is minus 1 to the power I plus j Mij. I think it's going to be easier to understand if I do an example. Let capital A be the 3 by 3 matrix 3, 1, minus 4, 2, 5, 6, 1, 4, 8. And I want to find four things. I want to find the minor of entry A11, the cofactor of entry A11, the minor of entry 32, and the cofactor of entry A32. So first, let's look for the minor of A11. The first number tells us the row, and the second number tells us the column. So that's first row and first column. We need to cross these out or delete these from the matrix. So there we are. And then we're left with a 2 by 2 matrix. The minor of entry A11 is the determinant of the 2 by 2 matrix that we're left with. So M11 is the determinant of the matrix 5, 6, 4, 8. And we know how to do determinants of 2 by 2 matrices, so this is just 16. And then I want to find the cofactor of entry A11. So using the formula in the yellow box at the top, it's going to be minus 1 to the power I plus j. For us, I is 1 and j is 1, so it's minus 1 to the power 1 plus 1 of M11. So minus 1 squared multiplied by 16, which is 16. And then we were asked to calculate the minor of entry A32. That's the entry in row 3 and column 2. So we need to cross out row 3 and we need to cross out column 2. And that gives us, again, a 2 by 2 determinant. The determinant of the matrix 3 minus 4, 2, 6 is 3 multiplied by 6 minus minus 4 multiplied by 2. And that is equal to 26. And then we want the cofactor of entry A32. So we do -1 to the power 3 plus 2, M32, that's -1 cubed, or -1 multiplied by 26 is -26. Now, note that we always have that the cofactor of entry Aij is either plus Mij or it's minus Mij. How can we remember when it's plus and when it's minus without having to do -1 to the power I plus j? Well, think about a chessboard. This is an 8 by 8 chessboard, but we want the chessboard to be the same size as our matrix. So 2 by 2, 3 by 3, 4 by 4, whatever we need. And instead of the pieces on this chessboard, I want pluses and minuses. And the rule is that the top left square should always be plus. And then it should always alternate, plus, minus, etc. So, for example, in row 5, column 1, I have a plus. So C51 is equal to plus M51. But in row 3, column 4, there's a minus sign. So we know that C34 is minus M34. The checkerboard for a 2 by 2 matrix is this: plus, minus, minus, plus. Always a plus at the top left. So that means that C11 is plus M11. How do we get M11? We cross out the first row and we cross out the first column. That's just A22. And then C12, row 1, column 2, there's a minus sign here. So it's a minus M12. What do we get if we cross out the first row and the second column in the matrix we started with? We're just left with the 1 by 1 matrix A21, and the determinant of that is just A21. So C12 is minus A21, etc. Now, note that we know the determinant of a 2 by 2 matrix is A11, A22 minus A12, A21. But look at in the yellow box at the top, A22 is the same as C11, and A21, or rather minus A21, is the same as C12. So this is the same as A11, C11 plus A12, C12. So in the matrix, we're just using the first column. We're using the entries in we're using the first row. The entries in the first row and the cofactors of the entries in the first row. But we don't have to use the first row. We could use a different row or a different column. For example, let's suppose we wanted to use the second row. I'm saying this is the same as A21, C21 plus A22, C22. Why? Well, look in the yellow box at the top. C21 is minus A12, and C22 is A11. So this is exactly what we started with. And then I'll leave it for you to check that the final two lines are also true. We could use the first column, A11, C11 plus A21, C21, or we could use the second column, A12, C12, A22, C22, and these will all be equal. The last four lines in this calculation are called cofactor expansions of the determinant of A. And in fact, this is true for any size, not just for 2 by 2 matrices. If A is just any square n by n matrix, then regardless of which row or column of A we choose, the number we get by multiplying entry cofactor plus entry cofactor plus entry cofactor plus entry cofactor, whichever row, whichever column we choose, we always get the same number. So that's how we define the determinant of some n by n matrix. Whichever number we get by choosing a row or choosing a column and doing entry cofactor plus entry cofactor plus dot 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 plus entry cofactor, this number is called the determinant of A, and the sums themselves are called cofactor expansions of A. So, for example, if we decide we're going to use the jth column, then we would get the cofactor expansion where the second number of everything is j. So A1j, C1j, and then we increase the 1 to 2, A2j, C2j, plus A3j, C3j, plus A4j, C4j, etc. Or, if we decide we're going to use a row, the ith row, then the first of these indices is always going to be I. AI1, CI1, plus AI2, CI2, plus dot dot dot, plus AIN, CIN. And by the theorem, it doesn't matter which row we choose or which column we choose, we always end up with the same number. Now, let me just remark that, as I've said previously, it doesn't matter if we use square brackets or rounded brackets when we write matrices. These two things mean the same thing. These are equal. These are exactly the same matrix written in two different ways. Just depends on which book you happen to read. Your textbook uses square brackets, so I'm using square brackets in this course. However, if we instead use vertical lines, then it doesn't mean a matrix, it means a number. It means the determinant of the matrix. Just be careful when you write your exam questions to be clear, are you writing square brackets or are you writing vertical lines? For example, find the determinant of the 3 by 3 matrix given here, and we're told that we should use cofactor expansion along the first row. Okay, so let's bring up the checkerboard for a 3 by 3 matrix. The top left is always plus. So our top row goes plus, minus, plus. So I could write these in first. Plus, minus, and then plus. And then I want to use the numbers or the entries in the first row. The green numbers here are 3, 1, 0. Let's write these in. It's plus 3, minus 1, plus 0. And then we need the minors of each entry. Not cofactors, because we've already put the pluses and the minuses. We need the minors. The minor of entry A11, we cross the first row and the first column out. We're left with the determinant of minus 4, 3, 4, minus 2. And then I need the minor of entry A12. So I cross out the first row and I cross out the second column. I'm left with minus 2, 3, 5, minus 2. So we need that determinant. And then finally, cross out the first row and the third column. We're left with minus 2, minus 4, 5, 4. So that's 3 2 by 2 determinants we need to calculate. And I'll leave this for you to check. Check that after we calculate these 3 2 by 2 determinants, put them into the calculation, the answer that we get is minus 1. Next example. Find the determinant of the same matrix by cofactor expansion along the first column. So first of all, let's look at the first column of the checkerboard. The first column goes plus, minus, plus. And the entries in the first column of our matrix are 3, minus 2, 5. So we can put these in. Plus 3, minus 2, plus 5. And then we need to put in the minors of each entry. And then we need to calculate the determinant of these 3 2x2 matrices. And again, I ask you to check my calculation. I think that again we get minus 1. Of course we should, because the theorem says it doesn't matter which row or which column we choose, we should always get the same answer. Sometimes it's easier to use cofactor expansion along some rows or columns than others. For example, I want to calculate the determinant of this 4x4 matrix. So the first thing to decide is which row or which column are we going to use? And for this one, have a look at the second column. This has got the most zeros. It's going to be easiest for us if we choose this column. So second column of the checkerboard goes minus, plus, minus, plus. And our numbers are 0, 1, 0, 0. So it's going to be minus 0 plus 1 times the minor of entry A22 minus 0 plus 0. So we only need to calculate the determinant of this 3x3 matrix. Now look at this 3x3 matrix. Which row or column should I choose? Which row or column has the most zeros in it? And the answer is column 2 has the most zeros. So this is the one I'm going to use because this will be easiest. There will be least amount of work to do. Looking at column 2 of my checkerboard and looking at the green numbers, I have minus 0 plus minus 2 multiplied by the determinant of the 2x2 matrix, minus 0. So all I need to do is calculate the determinant of the 2x2 matrix and then multiply it by minus 2. And in fact, the answer is minus 6. Calculate the determinant of a 4x4 lower triangular matrix. Let me just remind you that if we have zeros up at the top, above the main diagonal, then it's called lower triangular. Again, I'm going to use cofactor expansion. Each time I'm going to be using the first row. The first row of this matrix has A11 and then it's 0, 0, 0. So it's going to be the least work. Because the top left square in the checkerboard is always plus, it's going to be plus A11, and then we're going to have the determinant of a 3x3 matrix. But then I'm going to use the first row again, because the first row has 2 zeros. So it's going to be A11, A22, multiplied by the determinant of a 2x2 matrix. And we know how to do 2x2 determinants. The answer is just A11, A22, A33, A44. And that's always the case for a triangular matrix. It's always the product of the entries on the main diagonal. Let's write that as a figure. If A is an n by n triangular matrix, and it doesn't matter which type. It might be upper triangular, it might be lower triangular, or it might be diagonal, because diagonal matrices are also triangular. Then the determinant of A is A11, A22, A33, A44, A55, etc., up, finishing up to ANN. Briefly, I want to talk about the rule of Saras. This is a shortcut or a different way to calculate the determinant of a 3 by 3 matrix. We know how to do 2 by 2 matrices. We know that we do A11, A22, and we call these plus, and we do A12, A21, and then we do minus them. We could do the same idea for a 3 by 3 matrix. We need to copy the first 2 columns over to the right, and then arrows which point to the right we say are positive, arrows which point to the left are negative. More precisely, we sum the products on the rightwards arrows and then we subtract the products on the leftward arrows. Now, just warn you, this rule only works for 2 by 2 and 3 by 3 matrix. Don't try to use it for bigger matrices. Every semester when we look at the exams, there's always at least one student that tries to use this rule for a bigger matrix and they get the wrong answer. Don't be that student this time. It doesn't work for bigger matrices. So for example, here's something I took from a textbook. I'm just interested in the second calculation. First, we copy the first 2 columns, A1 minus 4, 7, and 2, 5 minus 8, and we write them on the right of the determinant. And then we do plus for each of the rightward arrows and minus for each of the leftward arrows. So for example, the first rightwards arrow, 1 multiplied by 5 multiplied by 9 plus 45. And then 2 multiplied by 6 multiplied by 7 plus 84, etc. And then when the arrows go to the left, it's minus. So for example, 3 multiplied by 5 multiplied by 7 is 105, so minus 105, etc. Our next topic is evaluating determinants by row reduction. Theorem: if A has a row of zeros or a column of zeros, then the determinant of A is equal to 0. Why? Let me prove this to you. And I'm just going to prove it for the left matrix above, because the idea is the same for any matrix. The left matrix above has row 3 as all zeros. I want to do cofactor expansion along the third row. If I do this cofactor expansion, it's 0C31 plus 0C32 plus 0C33 plus 034 plus 0C35 plus 036. So 0 plus 0 plus 0 plus 0 plus 0 plus 0, which is 0. The same idea we could use for any square matrix which has a row of zeros or a column of zeros. Next theorem. The determinant of A is equal to the determinant of A transpose. Why is that true? Well, remember what happens when we do the transpose of a matrix. What we do is we swap columns to rows and we swap rows to columns. So that means cofactor expansion along the ith row of A is exactly the same as cofactor expansion along the ith column of AT. So if we're doing the same calculation for each matrix, that means they must have the same determinant. Next, I want to explain how the elementary row operations affect the determinant of a matrix. What happens if we multiply a row by a number k? Let's do cofactor expansion along the first row. So it's going to be ka11, c11 plus ka12, c12 plus ka13, c13. Factor out k, and what do we have? We have k multiplied by the cofactor expansion along the first row of this matrix. That means multiplying a row of a matrix is the same as, and then calculating the determinant is the same as calculating the determinant first and then multiplying by k. And what happens if we swap two rows of a matrix? Well, if we swap two rows, the numbers in a matrix stay the same. But look at the checkerboard on the right. What happens if we swap the first row and the second row of the checkerboard? Pluses swap with minus signs. So when we do our calculation, we're going to get minus. Now, some of you might be thinking, wait a minute, what happens if we don't swap two rows next to each other? Well, let's suppose that we swap the first row and the third row. Then the checkerboard stays the same, right? Yes, the checkerboard stays the same, but what happens if we try to calculate the minor of entry A11? For the original matrix, the matrix on the left, if we're calculating the minor of A11, we cross out the first row and we cross out the first column. In the second matrix, if we're trying to calculate the minor of the same entry, we cross out the third row and the first column. And then look what we're left with. We're left with plus, minus, minus, plus over here, but on the right, we're left with minus, plus, plus, minus. So again, pluses are changing to minuses and minuses are changing to pluses. So again, we still get that the determinant of our new matrix is equal to minus 1 multiplied by the determinant of the matrix we started with. And what happens if we add a multiple of one row to another row? Cofactor expansion along the first row, and then separate the terms like this. I have the determinant of the matrix we started with plus k times a new number, A21, C11 plus A22, C12 plus A23, C13. But what is this new number? Let's calculate this. I'm not going to go through all the details here. I'm leaving this for you to check. You can check that C11 is A22, A33 minus A23, A32, etc. And also look at these terms which I put in green. The first one is plus A21, A22, A33. And then the second green term is minus. Change the orders, A21, A22, A33. These are exactly the same. These are going to cancel out. In fact, I'll leave it for you to check that every term cancels out and we're just left with 0. So that means adding a multiple of one row of a matrix to another row does not change the determinant. I've done that for 3 by 3 matrices, but that's true for any square matrices. Let's write it as a theorem. Let's suppose we start with a matrix we call it A, and we're going to multiply one row by a number k to get a new matrix which we're going to call B. then the determinant of B is equal to K multiplied by the determinant of A. Rule number 2, if we swap 2 rows of A to make a new product B, and there's a typo here, this should be produce. If we swap 2 rows of a matrix, then we multiply the determinant by -1. And rule number 3, if we add a multiple of one row to another row to produce a new matrix B, that does not change the determinant. And I've written at the bottom, this is also true for columns. Multiply by a column by a number, we multiply the determinant by that number. Swap 2 columns, multiply the determinant by -1, add a multiple of one column to another column, no change. Let's just look at elementary matrices. Elementary matrices are matrices where we start with the identity matrix and we do one row operation. So for example, start with I4 and multiply row 2 by the number 3. We multiply the determinant by 3. The determinant of this B is equal to 3, the determinant of I is 1. Or if we swap 2 rows, we multiply the determinant by -1. Or if we do 7 times row 4 and we add that on to row 1, there's no change in the determinant. This one's easy to check because this is a triangular matrix, and the determinant of a triangular matrix is always the product of the entries on the main diagonal. So 1 multiplied by 1 multiplied by 1 multiplied by 1. Another theorem. If A is a square matrix with 2 proportional rows or 2 proportional columns, that means one row is equal to some number multiplied by another row, or the same idea for columns. If that's true, then the determinant of A is equal to 0. For example, look at these 3 matrices. First matrix, row 2 is 2 times row 1. Second matrix, column 2 is -2 multiplied by column 1. And in the third matrix, row 4 is -3 multiplied by row 1. In each of these matrices, one row or one column is equal to a multiple of another row or column. So the determinants must be equal to 0. Why? Well, let me show you an example. Remember that the elementary row operation 3 times row 1 plus row 4 goes to row 4 doesn't change the determinant of a matrix. And the second thing to remember is a matrix which has a row of zeros always has 0 determinant. So for this 4 by 4 matrix, if we do this row operation, the determinant doesn't change, and we end up with a matrix where row 4 is 0, 0, 0, 0. That's why if we ever have one row is a multiple of another row, or one column is a multiple of another column, then the determinant is always equal to 0. Next, I want to talk about how we can use row reduction to calculate the determinant of a matrix. For example, calculate the determinant of this 3 by 3 matrix. The technique I'm going to use is I'm going to row reduce this matrix to row echelon form. That means reduce it to an upper triangular matrix, and then we're going to calculate the determinant of the upper triangular matrix. So first I want to do the row operation swap row 1 and row 2. What happens to the determinant if we swap two rows? We multiply the determinant by -1. So we can write that the first determinant is equal to minus this new determinant. Then I'm going to multiply the first row by 1/3. We need to multiply the determinant by 3. Now, if you're unsure about this, just remember it this way. 3 minus 6 plus 9 is the same as 3 multiplied by 1 minus 2 plus 3. We're just doing the same thing here. We're factoring out a number if you wish. And then I'm going to do minus 2 row 1 plus row 3 becomes the new row 3. When we do that type of row operation, there's no change in the determinant. And then I'm going to do minus 10 row 2 plus row 3 becomes the new row 3. Again, no change in the determinant. And then I have an upper triangular matrix. To calculate the determinant of the upper triangular matrix, we just multiply the entries on the main diagonal. So 1 multiplied by 1 multiplied by minus 55. Let me show you another one. Calculate the determinant of this 4 by 4 matrix. And this time I'm not going to give all the details. I'm going to leave this for you to come back later and check the details here. The first row is all even numbers. I can take a factor of 2 out, and the first row then becomes 1 minus 4, 3, 4. And then after that, every row operation I'm using is just multiple of one row added to another row. So after that, the determinant does not change. I'll leave the details for you to check. I want to end up with an upper triangular matrix because it's easy to calculate the determinant of an upper triangular matrix. It's just 1 multiplied by 3 multiplied by minus 6 multiplied by 1. Sometimes we can combine these two methods. We can use row reduction and cofactor expansion. For example, calculate the determinant of this matrix. The idea is we use row reduction so that we get a row or a column with lots of zeros in, and then we use cofactor expansion to change our determinant into the determinant of a smaller matrix. So first I'm doing 3 row operations all at the same time, and I'm doing it so that I can get 3 zeros in the first column. And then I switch to my other technique. I do cofactor expansion on the first column. 0, 1, 1 has a minus in front of it, 0, 0. So it's going to be 0 minus 1 multiplied by C21 plus 0 minus 0. At this point, we just have the determinant of a 3 by 3 matrix. Switch back to the row reduction technique to get some zeros. Row 1 plus R3 becomes a new row 3. And then again, first column has 2 zeros and one number which is not 0. So now it's time to do cofactor expansion on the first column. Bring up the checkerboard. It's a plus in the same position as the minus one, and then we just have 0 and 0. So it's going to be minus and then plus minus 1 multiplied by the determinant of a 2 by 2 matrix, which is then easy to calculate. The answer is just minus 18. One more example before I take a break. And this is an exam question from 2017. If you look at the past exam papers I posted in the course content section, you will find this question in 2017. Suppose that the determinant of the matrix A, B, C, D, E, F, G, H, I is equal to 7. Use that information to calculate the determinant of these two new matrices. Let's look at the first one. How do we go from the matrix that we know to this one? The answer is we swap the first two rows. And what happens to the determinant when we swap two rows? We multiply the determinant by minus 1. So straight away we can write down that the determinant of the matrix DEF, ABC, GHI is minus 7. That leaves us with the second one. How do we go from the first one to the second one? Well, we multiply row 2 by 2. What happens to the determinant if we multiply row 2 by 2? We multiply the determinant by 2. So the determinant of the matrix ABC, 2D, 2E, 2F, GHI must be 2 times 7, or 14. We're not finished yet. We also need to add row 1 to row 2. And what happens if we add a multiple of one row to another row? The determinant does not change. So the determinant of the matrix that we want is also 14. And now that brings us to a good place to take a break. We're going to take a 10-minute break, and then I'm going to continue talking at 3 o'clock. And now let's continue. I want to talk about some properties of determinants. What is the determinant of Ka? What is the determinant of A plus B? What is the determinant of A multiplied by B? Well, the first thing to notice is that if we multiply a determinant by a number K, we know what happens if we multiply a row by K. We can take the red K out of this determinant, and then we can take the green K out, and then we can take the orange K out. We get K cubed multiplied by the matrix that we started with. And this is our theorem. If A is an n by n matrix, and if K is a number, then the determinant of K multiplied by A is not K multiplied by the determinant of A, it's K to the power n multiplied by the determinant of A, because each row gets multiplied by K. So we have n factors of K. And what do we get if we do A plus B? For example, if A is the 2 by 2 matrix 1, 2, 2, 5, and B is the 2 by 2 matrix 3, 1, 1, 3, we can add them together to get the matrix 4, 3, 3, 8. But note the determinant of A is 1, the determinant of B is 8, and the determinant of A plus B is 26. There's no connection between these numbers. The determinant of A plus B is not the same as the determinant of A plus the determinant of B. And that's true in general. There is one special case that we could consider, and that's when two matrices are the same except for one row. So for example, have a look at the matrix A and the matrix B. They have the same first row, so there's only one row which is different, only the second row is different. If we then do determinant of A plus the determinant of B, and I'll leave this calculation for you to check, we get the determinant of the 2 by 2 matrix A11, A12, A22 plus B22, A21 plus B21. There's a typo there, of course. These bottom two should be swapped around. So what that means is, if we have three matrices which are the same except there's just one row difference between them, and let's suppose that that row of C could be made by adding the after rows of A and B together. In this special case, the determinant of C is equal to the determinant of A plus the determinant of B. And the same is true for columns. But in general, adding two matrices together, there's no connection between that, the determinants of between their determinants and the determinants of the new matrix. I'm going to ask you to check that the following calculation is true. The determinant of the matrix 1, 7, 5, 2, 0, 3, 1 plus 0, 4 plus 1, 7 plus minus 1 is the same as the sum of these two determinants. Note that all three matrices have the same row 1 and have the same row 2. And if we do row 3 plus row 3, we get row 3 on the left. This is the only special case when we can add determinants together. And then the most important theorem of today's lecture: a square matrix A is invertible if and only if the determinant of A is not equal to 0. So, for example, is the matrix 1, 2, 3, 1, 0, 1, 2, 4, 6 invertible? Note that row 1 and row 3 are proportional. Row 3 is equal to 2 times row 1. What do we know if a matrix has proportional rows? It means the determinant must be 0. If the determinant is equal to 0, then the matrix is not invertible, the matrix is singular. Let me just repeat this theorem because this is the most important theorem in today's lecture. A square matrix is invertible if and only if the determinant of this matrix is not 0. We will be using this fact throughout the rest of the course. Another theorem. The determinant of A multiplied by B is the determinant of A multiplied by the determinant of B. For example, if A is 6132 and B is 4312, then AB is 2520, 1413. I'll leave that for you to check. I'll also leave it for you to check that the determinant of A is 9, the determinant of B is 5, and the determinant of AB is 45. And 9 multiplied by 5 is equal to 45. Now, recall that A inverse multiplied by A is the identity matrix. And the determinant of the identity matrix is always 1. And using this fact we've just done, the determinant of the product of two matrices is just the product of the determinants. That means the determinant of A inverse multiplied by the determinant of A must be equal to 1. And if A inverse exists, then A is invertible, so then the determinant of A is not equal to 0. I could divide both sides of this equation by the determinant of A, and I get the formula. Determinant of A inverse is 1 divided by the determinant of A. Next idea, because the determinant of AA is the determinant of A multiplied by the determinant of A, the determinant of AAA is the determinant of A multiplied by the determinant of A multiplied by the determinant of A, and so on. We have the theorem that the determinant of A to the power n is the determinant of A all to the power n for any natural number n. So, for example, we might be asked to calculate the determinant of 2A cubed if A is the matrix 102, 114, 133. And this was actually an exam question which we asked in 2018. The idea is, first we're going to calculate the determinant of A, and then we're going to use the theorems on the previous slides to calculate the determinant of 2A cubed. So first, the determinant of A, row reduction, add the -1 times the first row to row 2 and row 3 so that we get 2 zeros here. And then do row 3 minus 3 times row 2 to get another 0. The determinant of a triangular matrix is easy. 1 multiplied by 1 multiplied by -5. And then we want to calculate the determinant of 2A cubed. Well, the first idea is if we have a number 2, we can take it outside of the determinant as long as we do it to the power of n, if we have an n by n matrix. Here we have a 3 by 3 matrix. So if we take the 2 outside of the determinant, it has to become 2 cubed. And then what is the determinant of A cubed? That's just the determinant of A all cubed. So the calculation is just 8 multiplied by minus 5 to the power 3, or minus 1000. Or if you wanted to, you could calculate 2a cubed. You could do a multiplied by a multiplied by a, and then double it, and then calculate the determinant. But that would be a much longer calculation. Let A, B, and C be 4 by 4 matrices, where the determinant of A is 1, the determinant of B is 2, and the determinant of C is 3. Find the determinant of 3a to the power minus 1, B transpose C squared. Let's split this up. Remember, we have a 4 by 4 matrix. So if we take the number 3 outside, it becomes 3 to the power 4. And then we can split it up to the determinant of A inverse, determinant of B transpose, determinant of C squared. What is the determinant of A inverse? That's just 1 divided by the determinant of A. What is the determinant of B transpose? We talked about that earlier. That's exactly the same as the determinant of B. Taking a transpose does not change the determinant. And the determinant of C squared is the same as the determinant of C all squared. And that's most of the work done. Just put in the numbers 1, 2, and 3 and calculate the answer. I'm not going to finish this. Next, I want to talk about the adjoint of a matrix. Let's suppose A is an n by n square matrix, and let Cij denote the cofactors of A. If we write down the n by n matrix, where each of the entries is the cofactor of the matrix that we started with, this is called the matrix of cofactors from A. And then if we take the transpose of this matrix, we get a matrix which is called the adjoint of A. And we write that as ADJ of A. So for example, find the adjoint of this matrix. There's 3 steps here. We're going to need to find all of the cofactors of A. We're going to write them in a matrix. We're going to write down the matrix of cofactors. And then step 3, we're going to take the transpose. So first, the cofactors. Let's talk about some of these. The cofactor of the first one, cross out row 1, cross out column 1. The determinant of the matrix 6, 3 minus 4, 0 is plus 12. And because we have a plus in our checkerboard, it's going to be plus 12. And so on. I'll leave the rest of them for you to check. And then we take these 9 numbers and we write them in a matrix. That's the matrix of cofactors. And then finally, we need to take the transpose of this matrix. And then we obtain the adjoint of A. Why are we interested in the adjoint of A? Because of this formula. If A is an invertible matrix, then A inverse is equal to 1 divided by the determinant of A multiplied by the adjoint of A. So for example, use this theorem to find the inverse of this capital A. We've already found the adjoint of A, so we just need to calculate the determinant of A, and then we're going to do 1 divided by the determinant of A multiplied by the adjoint of A. I've showed you lots of different ways to calculate the determinant of a matrix. For example, we could use cofactor expansion along the first row. I'll leave this for you to check. we get 64. There's a typo here as well, of course. This should be true. After we've got the determinant and after we've got the adjoint of A, we can calculate A inverse. It's going to be 1 divided by 64 multiplied by the adjoint of A. Or 12 over 64, 4 over 64, 12 over 64, etc. Another example, an example I've taken from a textbook. Find the inverse of the matrix 2, 1, 3, 1, minus 1, 1, 1, 4, minus 2. Step 1, find the cofactors. Step 2, write down the cofactor matrix or the matrix of cofactors and then take its transpose. I'll leave these cofactors for you to calculate, and then after we've got those, we can write them in the adjoint of A. So for example, minus 2, 14, 4 becomes row 1. Minus 2, 14, 4. Then we need the determinant of A. I'll leave it for you to check that the determinant of A is 14. So then it's 1 over 14 multiplied by the adjoint of A to get the answer to this calculation. Let me move on quickly. You can come back later and read this. Our fourth and final topic for today's lesson is Cramer's rule. First, some notation. Let's suppose we have an n by n matrix and an n by 1 vector. What I want to do is I want to replace the first column of A by B, and then I'm going to call this new matrix A1. So take the first column of A and delete it, and then we're going to replace it with B. Or let's suppose instead of the first column, I want to use the second column. If I replace the second column of A by B, I'm going to call this new matrix A2. And so on. Replace the third column to get A3, and so on. If I replace the nth column of A by B, I'm going to get a new matrix which I'm going to call AN. Now let's talk about Cramer's rule. Cramer's rule says if AX equal to B is a system of n linear equations in n unknowns with n variables, so same number of equations as variables, and if the determinant of A is not equal to 0, then this linear system has a unique solution, which is given by these formulae. x1 is the determinant of A1 divided by the determinant of A. x2 is the determinant of A2 divided by the determinant of A, and so on. Let's write these formulae in a yellow box. I want to use Cramer's rule to solve 3x1 minus 2x2 is equal to 6, 5x1 plus 4x2 is equal to 8. So what do we have here? A is 3 minus 2 minus 5, 4, and B is the vector 6, 8. Take A and replace the first column by B to get A1 is 6 minus 2, 8, 4. Or take A and replace the second column by B to get A2, 3, 6 minus 5, 8. What is the determinant of A? The determinant of A is 2, which is not 0. So by Cramer's rule, this linear system has a unique solution. And also by Cramer's rule, we can use the formula in the yellow box at the top. We have a 2 by 2 matrix, so only the first two. x1 is the determinant of A1 divided by the determinant of A, and x2 is the determinant of A2 divided by the determinant of A. So x1 is 24 plus 16 divided by 2, or 20, and x2 is 24 plus 30 divided by 2, or 27. Now, Cramer's rule is useful if you only want to find some of the variables and you don't care about the rest. Instead of doing row reduction to find the solutions of all of the variables, let's suppose we only want one or two of them. Let's suppose we have an example like this. Find x3 if it's x1, x2, and x3 satisfy this linear system. So here we have the matrix A is 1, 0, 2, minus 3, 4, 6, minus 1, minus 2, 3. B is the vector 6, 38. And if we take A and replace the third column by B, we get A3 is 1, 0, 6, minus 3, 4, 30, minus 1, minus 2, 8. I'm going to leave it for you to check that the determinant of A is 44 and the determinant of A3 is 152. By Cramer's rule, because the determinant of A is not 0, the linear system has a unique solution, and x3 is the determinant of A3 divided by the determinant of A. 152 divided by 44. Consider the following system in which S is some unspecified parameter. Determine the values of S for which the system has a unique solution and use Cramer's rule to find the solution. 3sx1 minus 2x2 is equal to 4, minus 6x1 plus sx2 is equal to 1. So we can write down our A, our A1, and our A2. And we can calculate that the determinant of A is 3 times s plus 2 multiplied by s minus 2. The linear system has a unique solution if and only if the determinant of A is not 0. So there's a unique solution when s is not plus 2 and a unique solution when s is not minus 2. And then using Cramer's rule, we can find the solutions. x1 is the determinant of A1 divided by determinant of A. Oh, there's a typo here as well. This should be an S. x1 must be 4s plus 2 divided by 3s plus 2s minus 2. And x2 is the determinant of A2 divided by determinant of A. S plus 8 divided by s plus 2, s minus 2. And that's the end of the theory for today's lesson. I'm going to finish today's class by looking at a past exam paper. This is linked in the course content section. This is the first midterm exam from the 4th of November 2019. And I want to talk about all 4 questions from it, because I think now you should be able to answer all 4 questions. Question 1, for which values of k does this system have no solution, infinitely many solutions, or a unique solution? The idea is we're going to write the augmented matrix, and then we're going to row reduce it, and we're going to look to see where are the pivots. So I'm not going to go through the calculations. Let's just suppose that the calculations is correct, and this is what we get. What are the important values of k here? Well, we have a k minus 1. So it looks like k equal to 1 is an important number. And we also have 2k minus 1. How could that be 0? It could be 0 if k is a half. So it looks like k equal to a half is an important number. And again, 1 minus 2k, again, that gives k equal to a half. So we're going to see what happens if k is equal to 1, what happens if k is equal to 2, and what happens for other numbers if k is not 1 and k is not 2. First of all, what happens if k is equal to 1? Then the third row becomes 0, 0, 0, minus 1. We have a pivot in the right-hand column. What happens if we have a pivot in the right-hand column? We know that the system does not have any solutions. It's an inconsistent system. What happens if k is equal to a half? K is equal to a half. The bottom row is 0, 0, 0, 0. There's 2 pivots, so that's 2 basic variables and 1 free variable. That means the system has infinitely many solutions. And then finally, if k is not 1 and k is not a half, we can row reduce the matrix a little bit further. And then we can see that there's 3 pivots. That means 3 basic variables and no free variables, so there must be a unique solution. Let's move on to question 2. Calculate the determinant of this 4x4 matrix. Use any method you wish. Remember, for a 4x4 matrix, you can't use the rule of Serres. That only works for 2x2 and 3x3 matrices. So your techniques are either do cofactor expansion along a row or a column, or use row reduction, or use a mixture of those 2 methods, which is what's done here. The person that wrote this has used row reduction so that column 2 has 3 zeros, and then they're doing cofactor expansion along the second column. They end up with a 3x3 determinant. And then they use row reduction again, so that the first column now has 2 zeros in. And then they do cofactor expansion along the first column. And they get the answer 16. And then part B of this question, this is the same matrix. Sorry, it's not the same matrix, it's almost the same matrix. Suppose that AX is equal to B, where A is this matrix and B is the vector 2, 0, minus 2, 0. And crucially, we're told that the determinant of A is -2, which is going to save us some work. Use Cramer's rule to find x2. Cramer's rule says x2 is the determinant of A2 divided by the determinant of A, and we already know the determinant of A. So all we need to do is the determinant of A2. But that's the matrix we've just done. This is A2. And the determinant of this matrix is 16. So because we've already found the determinant of A2, and because we're told that the determinant of A is -2, all we have to do here, the whole calculation here, is 16 divided by -2. 16 divided by -2 was worth 10 points in that example. Question 3. Find the adjoint matrix of this matrix. So as we talked about earlier, we need to all of the cofactors. So that's the long part of the calculation. We need to do 9 2x2 determinants, and then we need to work out if each one is plus or minus. We could either do -1 to the power I plus j, or we could do our checkerboard. We could write plus, minus, plus, minus, plus, minus, plus, minus, plus, and then we can see straight away if each one should be plus or should be minus. Then we write down the matrix of cofactors. So that's just copying the numbers down. And then the third and final step is to take the transpose of that matrix to get the answer. And then part B was to find the inverse of A. This is the same A as in part A. We've already found this adjoint. This is a triangular matrix. It's very easy to find the determinant of a triangular matrix. So all we need to do is 1 divided by the determinant multiplied by the matrix that we found in part A. So that's very, very easy, 15 points. That's even easier points than the previous question, perhaps. Or if you don't realize that it's the same matrix that's in part A, you could use the other method that we've talked about to find the inverse of a matrix. We could start with AI, the augmented matrix with A on the left, I on the right, and then we could row reduce this, and we end up with A inverse. And then we can read it off. That's a longer calculation, but it's not too hard. It's not as easy or as quick as using the first method. And then question 4. 4a, I don't want to spend a lot of time thinking about. It's not something really to teach. I think there's no important theorems or concepts here. It's just playing with an equation. It's just algebra. It's just manipulating the equation. Instead, let's look at question 4b. We're told that A, B, and C are 3x3 matrices. The number 3 is going to be important. We're told that the determinant of A is -3, the determinant of B is equal to 4, and the determinant of C is equal to 2. And then we're asked to calculate the determinant of 2a squared, b to the power -2, c transpose. So what can we do? The first thing to remember is that if we have a number, a constant multiple or a scalar multiplying our matrix, we can take it outside the determinant, but it always has to be to the power of n, where if you have an n by n matrices. We have 3 by 3 matrices, so it's going to be 2 to the power 3. And then we're going to have determinant of A squared. And then it's b to the power minus 2, so it's 1 divided by the determinant of b squared. And then the fourth thing to remember is the determinant of C transpose is the same as the determinant of C. So put the numbers in. 2 cubed is 8. Determinant of A is minus 3, so minus 3 squared. And then 1 divided by the determinant of B squared, so 1 divided by 4 squared. Multiply it by 2 because that's the determinant of C. 15 points for just doing 8 multiplied by minus 3 squared, multiplied by 1 over 16, multiplied by 2, and getting the answer 9. I think that's another quite easy 15 points on this exam. And that is the end of today's lesson. Are there any questions about today's lesson or a previous lesson? In part A, we calculated the determinant of this matrix. It was called A here, but in the notation of part B, this is the matrix A2.